Until about 200 years ago, we humans largely depended for our energy needs on our own muscles, on animals, and on burning wood. When we ran short of wood, we discovered a marvelous source of energy stored in fossil fuels: coal, gas, and oil. Fossil fuels are nothing more than the transformed remains of plants and animals that died millions of years ago. When we burn them, we release the energy of the ancient sunlight that helped create them in the first place. But we have come to be dangerously dependent on fossil fuels, even addicted to them. Not only does that accelerate global warming, we're likely to run out of cheap oil and gas by mid-century. Coal, though much more abundant, is highly toxic. So we must do something urgently. In the developed world, we must learn to use less energy. A 50% reduction may be necessary. And we must turn increasingly to renewable energy sources. One of our most promising solutions may be to turn back to our old friend, the sun. Do you know that the solar energy that strikes the Earth's surface for 1 hour is enough to feed the world's current electricity needs for 1 year? So why haven't we gone solar already? I mean, it's pollution-free, there's no global warming, there's no dependence on foreign oil powers, it's decentralized, so it's virtually terrorist-proof, and effectively, there's an infinite supply. I mean, it sounds like the dream solution, doesn't it? But will it work? This film's all about sunlight, what it is, how we are learning to use it, and what the future may hold. Our story starts, however, long ago and far away. Many ancient peoples worshipped the sun. The Egyptian pharaoh Akhenaten founded the first religion in history to have a single god, and that god was the sun. The writers of the Bible acknowledged its primacy by having God's first instruction be, "Let there be light." But what exactly was this stuff, light? No one had any clear idea until the eminent English scientist Isaac Newton took an educated guess about 300 years ago and wrote, "Are not the rays of light very small bodies emitted from shining substances?"
Well, Newton's idea of light was really quite a simple one. He thought that light consisted of a stream of particles that, as he knew, traveled in straight lines.
Newton's guess was a good one, as Einstein would later show. But a very different guess was made by a Dutchman, Christian Huygens. Huygens observed the waves made by a stone dropped in water. He had a brilliant insight, suggesting that light, as he said, spreads by spherical surfaces and waves. Here's a drawing that Huygens made to illustrate waves of light flowing from a candle. Huygens had created the wave theory of light, but like Newton, he couldn't back up his theory with experimental results. And so things stood until 1803, when a Londoner called Thomas Young was invited to make a presentation on light in the famous lecture theatre at the Royal Institution.
The Royal Institution was founded in 1799, immediately a big hit. People came to be educated, to learn about science. It was almost evidently like a magic show.
These physics students at Stanford University are replicating one of Thomas Young's experiments.
a ring stand for the laser.
Light from a single source must enter two narrow slits and eventually hit a screen some distance away. The reason that Young did this experiment was to try to see if light was a wave or a particle. Was Newton right or Huygens? The light from each slit spreads out like waves of water. Each wave interferes with the others, creating a pattern of light and dark patches.
All across that second screen, its intensity varied across the screen in a very regular way. And that could be perfectly naturally explained by the wave theory and couldn't be explained at all by Newton's theory.
So Christian Huygens' theory was right. Light is a wave. But that's not the end of the story. In the early 19th century, no one thought there was much connection between light, electricity, and magnetism. They seemed like three very different phenomena. Then, here at the Royal Institution, a young scientist called Michael Faraday started doing experiments with an electromagnet, and he discovered that electricity and magnetism were two sides of the same coin. Another British scientist, James Clerk Maxwell, then set out to formulate Faraday's findings mathematically, and his equations predicted the existence of electromagnetic waves.
So Maxwell discovered electromagnetic waves mathematically. He calculated the speed of these waves, and he noticed that it was exactly the same as the speed of light that had previously been measured. So suddenly, he finds himself confronted with this fact that light is a wave phenomenon, and it is an electromagnetic wave phenomenon. One of the great insights of natural science.
German scientist Heinrich Hertz experimented by shining lights on electrical circuits, and results seemed to confirm Maxwell's theory. Our knowledge is complete, said Hertz. A refutation of these views is unthinkable. The wave theory of light is a certainty. However, Hertz's assistant, Philipp Lenard, decided to look more closely at one of the experiments where there was a gap in the electrical circuit.
Different colors across the gap. Right now there's no high voltage, so you don't see anything happening. Let's go ahead and fire up the high voltage.
Okay.
Lenard found that if he shone light at low frequencies, red, green, or blue, on these two metal balls, nothing happened. But if the light was above a certain frequency, into the ultraviolet, electrons escaped from the metal and jumped across the gap, completing the circuit and creating a spark. Now, that didn't sound like the action of a wave.
Now, this doesn't make any sense, a threshold, a sudden change going from violet to ultraviolet, if light is a wave, smooth and continuous in how it delivers its energy. But if light is a particle, a threshold makes a lot more sense.
Here was an incredible paradox, because so many experiments could apparently only be explained by the wave theory, but here there was this new class of experiments that could very easily be explained by particle theory, but not by the wave theory. What to do with this?
No one could have predicted the problem would be solved by a patent office clerk in Switzerland. But that's what Albert Einstein was when he came up with the answer. In 1905, Einstein had the revolutionary insight that light has a dual nature. In some contexts, as Maxwell and Hertz had shown, it was a wave. But in others, as in Lenard's measurements, it consisted of discrete quanta of energy, or photons. The higher the frequency, the greater their energy. Amazingly, Newton and Huygens had both been correct. An experiment using modern equipment at Stanford shows very clearly that Einstein was right.
What we want to do is we want to observe single photons. So what we have here is we have a very sensitive photodetector, and it's connected to these optics through this fiber optic cable, which basically just funnels light into the detector. So we actually need to cover up these optics, and we need to actually shut the room lights off. And I'll use this flashlight as a light source to get photons into the detector.
In darkness, you hear no evidence of photons striking the detector. As the light becomes stronger, you hear a growing rush of photons. When the light is dimmed, there are fewer and fewer photons reaching the detector until you begin to hear the photons one by one.
So this shows that Einstein was right, and light is indeed made up of particles.
But nobody else could understand how light could be both a wave and a particle, not even the famous physicist Max Planck.
We know today the letter that Max Planck wrote to recommend Einstein. And in this letter he says many complimentary things about Einstein. And then he comes to Einstein's theory of the photon, and he says, you should forgive Einstein. Even a very great man can make a big mistake occasionally. And of course, eventually Einstein got his Nobel Prize for that work.
It wasn't relativity that won him his Nobel Prize, it was what he called the photoelectric effect.
The photoelectric effect is really the stroke of genius. It took courage, of course, also took insight and this genius touch, as I emphasize again, that transcends simple analysis and mere logic. And that is what is truly great about this great mind.
The entire history and development of modern work on solar electricity depends on Einstein's understanding of this photoelectric effect. In this context, light consists of lots of individual packets of energy, ready to react with whatever they strike. Einstein's insight had set the stage for the future advent of solar power. In the mid-20th century, some of the greatest developments in applied technology were made at Bell Labs, the Bell Telephone Laboratories in New Jersey. Here, in 1947, William Shockley, John Bardeen, and others developed the transistor, the most important electronic discovery of the century. It was both a switch and an amplifier, and it transformed everything from telephones to computing.
It revolutionized everything. You can really speak of the world before the transistor and the world after the transistor.
Dr. Walter Cohn worked here as a young man in the 1950s.
Well, the first time I came to Bell Labs, it felt like in a very intimidating place. It was known to everybody in physics as the #1 laboratory in the world. My recollection is that there were approximately 3,000 people working here. You know, everybody was doing his thing, but everybody was connected to other people who were doing their things.
It was this connection that brought together the work of 3 scientists to create the world's first practical solar cell.
Here are the inventors of the Bell Solar Battery.
Darrell Chapin was an electrical engineer. He'd been experimenting with early selenium cells for powering telephone lines in remote areas. A physicist, Gerald Pearson, was trying to develop a rectifier to replace mechanical telephone switching devices. And a chemist, Calvin Fuller, was working with the semiconductor silicon as part of the transistor project. Bell scientists liked silicon because of its electronic characteristics and because it was abundant. It's basically sand and makes up more than 1/4 of the Earth's surface. A single atom of silicon has 4 active electrons, which are called valence electrons. In a crystal of silicon, each of these valence electrons, together with a valence electron of a neighboring silicon atom, forms a bond joining those two atoms. However perfect it looks, solid silicon, like all semiconductors, doesn't work electronically unless a small fraction of the silicon atoms are replaced by foreign atoms called impurities.
Pure silicon is one of the dullest substances you could imagine. Does very little of interest. You introduce these minuscule fractions of impurities, and I say minuscule, part in a million, part in a billion atoms. Suddenly, all kinds of exciting things can be made to happen.
The chemist Calvin Fuller developed a highly controlled process for diffusing impurities into silicon. Take phosphorus, for example. It has 5 valence electrons, one more than silicon, and the core has one more positive charge than silicon. If you substitute an atom of phosphorus in a crystal of silicon, the extra electron, carrying a negative charge, will move around in the crystal. Silicon with these extra negative electrons is called N-type silicon. If you add a boron atom, which has one less valence electron than silicon, you are left with a missing electron called a hole. This too can move around in the crystal. Because the hole represents a missing electron, it has a net positive charge. This gives us P-type silicon. Gerald Pearson used Fuller's technique to make silicon rectifiers. He created something called a p-n junction. To make a p-n junction, you take a slab of silicon. You make one side of it N-type and the other side of it P-type. Between these two layers, a transition region develops with a permanent electric force field. Holes drifting into this region will get a kick to the P side and the electrons to the N side. And then something serendipitous happened. Pearson exposed one of his silicon rectifiers to a light source.
He shone some light on a piece of silicon with a p-n junction and discovered that he could get an unknown level of electric current, and realized immediately that this had tremendous implications.
So what was happening? Well, if you shine a light on a p-n junction, you are firing photons at it. Each photon excites one electron-hole pair. The electrons accelerate in one direction across the junction and the holes in the other. All that remained for Pearson was to complete an electrical circuit from one side of the silicon to the other, then shine a light and measure the electric current that flowed. It worked.
What I'm holding in my hands is the first battery, and it states the power that it produces. Not very impressive, but it's the beginning, 1/10 of a watt.
In this modern age, men have at last harnessed the sun with the Bell Solar Battery.
On April the 25th, 1954, Bell Telephone executives unveiled the new power photo cells.
Here are the inventors making a test of their newly harnessed power to operate a small radio transmitter.
This is a demonstration of the Bell Solar Battery in practical application. Do you hear me? Do you hear me?
And made an enormous impact on the press that understandably went overboard.
They had a huge press conference in New York. They had a light shining on the silicon solar cells, powering a little Ferris wheel that was made from an erector set. And the reporters who came had these great dreams that these little strips of silicon would produce more power than all the uranium, all the oil, and all the gas.
Here, this door was opened, and human imagination could see all kinds of future possibilities. But the first solar cells that were made were enormously expensive, so that the electricity that you got out of it was 1,000 times more expensive than the electricity you got from your standard power station where you burned coal or gas.
So what exactly could the miraculous new power source be used for? Because of their great expense and low power output, early solar cells seemed destined to remain a novelty, powering transistor radios and toys and a few highly specialized applications. The phone company, which had paid for the research, installed solar power experimentally on remote phone lines in Georgia. But was that all it could be used for?
It was just going to be thrown in the dustbin of history when the Pentagon came to Bell Laboratories.
It turned out that there was an application on the horizon right then and there for which the standard sources of electricity just were out of the question, and solar cells were exactly what was needed. And those were applications for space exploration.
In 1957, the Soviet Union launched the world's first man-made satellite, Sputnik, caused consternation in the US. The Soviets were in the lead in the so-called space race. But Sputnik stopped transmitting after several weeks for the simple reason that its batteries ran out. So, what was the alternative?
There were a variety of power sources, but they all died out over time. The batteries had to be recharged in some way, and they couldn't be recharged. It was a natural for solar energy. The satellite is up there in the sun all the time. Even if it's inefficient, there's energy that you can count upon. It was proof that this is a viable technology. It lasted longer than the satellites. This was the beginning of the new age of solar photovoltaic effect.
The eagle has wings.
By the time we went to the moon 10 years later, it was accepted wisdom that solar or photovoltaic cells were the best way to go.
The solar panel industry at that time for space was like a jewelry business. All the parts were made by hand, they were inspected multiple times. There were 300 steps in making every one, and each solar panel is a work of art. It's very special.
Reliability and durability were, and still are, the overriding requirements in space. The cost of solar panels is insignificant compared to the overall cost of a satellite. Today, solar-powered satellites connect vast numbers of communications networks. They coordinate transportation. They keep us informed on television. Nearly every cell phone call passes through solar-powered equipment. Modern life would be unthinkable without it. But down here on Earth, the bean counters are more rigorous. If solar is to be an option, it has to be more convenient or cheaper than what's already on offer. That's why, ironically, it was the oil companies that became the first major industrial users of solar power. Offshore oil rigs need electricity to run warning lights and horns, and there's no power grid out at sea. Solar panels combined with small storage batteries made practical and economic sense to the Coast Guard, too. Today, 99% of all their navigation aids, including lighthouses and buoys, rely on solar electricity. The more remote the location, the greater the need for photovoltaics. Railroads power distant switches and signals with solar panels. The phone company powers microwave relay stations in the mountains. And airfields can operate 24 hours a day wherever they are, thanks to handy devices like these self-contained blue landing lights.
A simple solar panel. The mountains are an excellent place to collect solar activity, and they use LED lights on the interior of the lens. A phenolic lens distributes that small amount of light to make it look like a regular taxiway light.
Here at California's Truckee Tahoe Airport, it would have cost them more than $1 million to connect their lights to the grid. Solar units cost just $135,000.
We also reduced the time for installation from 2 years to 1 month. In addition to that, the ongoing savings is about $18,000 a year.
The future of solar power for remote installations looks good. But will it become a major part of the world's energy mix? That depends on people like Terry Jester. She's worked in photovoltaics since the 1970s.
It was just an amazing time to be part of a group of people working 80, 90-hour weeks, feeling so committed and feeling like what we were doing and what we could do would change the world and change the future.
Terry Jester is Director of Operations at this factory, which is now owned by Shell. It has been making solar panels for more than 25 years. The whole time, the primary target has been to cut costs, to increase the efficiency of the solar panels, or to make them in a cheaper way. Shell is one of the oil companies that appear to take solar power seriously. They recently unveiled a large installation to power water pumps near Bakersfield, California.
This installation here of the Semi-Tropic Water District organization is a 1 megawatt system. The reliability of this product is one major technical reason to do something like this. As you can hear, you don't hear anything. There's no moving parts. In terms of environment, apart from no noise, it is also not polluting. It doesn't need any fuel, and the fuel is currently coming from above.
California and some other states have offered subsidies to business and homeowners to encourage the development of the industry. But it was in Japan that this idea really took off. In some ways, Japan is an extremely traditional society. It treasures beauty in everything it creates. This has been home to the same family for over 200 years. They still serve tea in the time-honored way, but Japan has other tastes too. Spend a few minutes in downtown Tokyo or Osaka, and you'll realize how deep is the Japanese love affair with technology and how much energy is required by this industrial superpower.
In Japan, we have very few natural energy resources. It is very important. We don't have so many coals, petroleums, natural gases, and uranium, etc. Therefore, we should create the energy by ourselves.
Because of Japan's needs for electrical independence and power independence, they had a large will to invest in solar power.
Sharp started researching in solar cell technology in 1959 and was the first to produce a solar cell in Japan. In 1961, Sharp became the first to apply solar technology to a consumer product by producing the solar-powered radio.
As with cars, Japanese companies came from nowhere and soon became world-class in electronics. Subsidies drove the market. This traditional Japanese house is now powered by solar panels.
For our children's generation, to keep clean environment is very important. This year, Kyoto Protocol becomes effective. So from now on, this becomes more important issues. Our dream is to install solar systems for all of Japanese houses.
All across Japan, modern apartment blocks and factories are sprouting solar panels. The secret of success in Japan was wholehearted government encouragement and subsidy.
The real change happened in 1994, where the Japanese government decided that they wanted to stimulate the growth of solar power in Japan to actually be an important part of the electrical distribution in the country.
But because the price of all electricity in Japan is so high, solar power is now almost competitive on price alone.
At the present stage, the Japanese government pays a subsidy of 5% for the solar system, as opposed to the 75% originally, but the number of people wanting to buy the systems continues to increase. So the systems are very close to being economic now.
This market today is driven really by two countries, Germany and Japan, and they've both taken a truly leading visionary role in driving the technology, in supporting the technology. Both countries have tremendous political support for clean energy, and to me it's a little bit ironic in that we could be looking in the future at importing solar panels just as we import oil today, because as a result of the markets being both in Germany and Japan, the industry, the centers of excellence have generally gravitated towards those two countries.
The Germans have embraced solar power as enthusiastically as the Japanese. What's called the world's largest solar installation was dedicated in June 2005 at Mühlhausen in Bavaria. It spreads over several acres and provides up to 10 megawatts of power for the electricity grid. This giant facility has been built as a commercial investment by a finance company. It cost more than $60 million. The company sees an enormous future for solar power. There are now more than 100,000 solar installations in Germany.
You can't go more than 5 or 6 miles without seeing a large array or a house with solar on it, so they've been really aggressively adopting solar in Germany.
But how seriously are we taking solar power in the United States? Dan Sugar is CEO of the Power Light Company in Berkeley, California. His car, of course, is electric.
Here we are driving in my electric car, 100% charged by solar electric technology, with off-the-shelf panels. There's nothing far out or Buck Rogers about what we're doing here. We're just driving an electric car charged by the sun.
It was Power Light which supplied much of the technology for the Mühlhausen installation in Germany. The company's principal product is an integrated roofing material, combining photovoltaic cells with a tough but very light form of insulation. They give buildings 3 benefits: electricity without monthly bills, a cooler environment in summer, and less need for heating in winter. This new approach, conservation-minded, carbon-free, could transform the prospects for solar power. But in the United States, the federal government is only now poised to offer a modest incentive. So the issue remains: cost. So, if solar power is so brilliantly effective, why haven't we seen a rapid transformation in our city centres? Cost, of course, has been the main problem.
$15 a watt was the best we could do when I was first starting out. Now, Shell Solar, they have much bigger wafers and much more automation, and they make and sell panels for about $3 a watt.
When we get into the $1 a watt to maybe $1.50 a watt range, we start becoming really competitive with almost all forms of energy. Right now we're competitive with various forms of energy, off-grid types of power.
But we know the prices are coming down. They historically have been coming down, and they will, we see very clearly that they will come down to where they won't be any longer 2 or 3 times as expensive. They will be competitive. At the same time, oil and other fossil fuels, the price will be increasing. We don't know exactly what year that will cross over, but it's not that far away, 10 years, give or take, right? So the question is, do we want that technology available when the price of oil starts to skyrocket or not?
Right now, however, people have to be convinced to go solar, one home or one business at a time. One of the things that convinces them is seeing an electric meter that runs backwards. This New Jersey family sells its unused electricity to the power company.
The electric company didn't believe that we were producing so much energy, so they came and they changed the meter once. They didn't believe it, they came and changed it again. We're now on our third meter from the electric company. It's now a digital meter, and we still get a fantastic high every time you see that meter going backwards. What this meter shows is the amount of energy we've produced and also the amount that we've sold. It shows that we've used 6,689 kilowatts from the grid, and by the same token we've sold back to the grid 3,996 kilowatts. On the bottom left-hand quadrant, you'll see that there are now boxes that are moving from the right to the left with a left arrow. That shows that we're producing excess electricity and selling it back to the grid. It's producing the peak usage during the middle of the day, and during the middle of the day, especially during the summer, is when everyone is turning the air conditioners on. So instead of having to put in another power plant here, we're able to use the sun's energy to not only power our home, but to power other homes during the day.
And that's why the state of New Jersey offers many incentives to install solar energy. Yes, this is still New Jersey, and this is indeed a sheep shearing shack. One thing that appeals to many farmers is the independence that solar power gives them. No need to depend on the power company or even on gas supplies at the pump.
This is a 7.2 kilowatt ground-mounted array. It's enough to power the house as well as the farm behind us, and it produces about 9,000 kilowatt hours of power a year.
So what it did was it added a lot to our mortgage, but it hopefully will eliminate the rising cost of power over time.
From an investment perspective, the numbers for a solar system are absolutely a no-brainer. If more people knew about it, we'd be selling more systems. So I think it's a matter of time getting the word out.
But of course, the numbers only add up because the taxpayers of New Jersey have chosen to subsidize solar energy. This is a recycling center in Santa Barbara, California. Everything comes here, not just the bottles and cans which you and I recycle, but great big chunks of building materials from demolition sites. Garbage companies aren't always renowned for their elegance or subtlety or social conscience, but this company has been family-owned from the start, 70 years ago. The family has decided to make sustainability a priority.
We didn't necessarily do it for financial reasons. We did it for the bigger picture. We're trying to set an example and get other people involved in it.
The price of land in Santa Barbara is so high that landfills truly are a waste of space. So Marburg is recycling more and more of the trash and powering more and more of the operation with solar panels.
We have put 3 systems in now, and this company, this family, we're committed to solar. We have examined the numbers. Long term, it certainly makes sense for more than one reason. It makes sense for a lot of reasons long term.
As solar power becomes fully competitive economically, these large industrial operations will change the picture of energy use in the United States. This is the world's biggest municipally owned solar array. It helps to power San Francisco's Moscone Convention Center, which spreads out under this roof. A team of British engineers are meeting with the city's manager of renewable energy, Fred Schwartz.
This was the first large array that the city has engaged in. And what we've done since that time is create what I call a pipeline of solar projects, where we're showing the citizens that we're switching from, in many cases, fossil-generated electricity to clean, locally generated sources, like this solar.
In England, with some of the gales we get, this is all blown to pieces.
Oh, well, this is rated at 120 miles per hour.
Right.
It's not going to blow, we did extensive wind tunnel testing, and it's not going to go anywhere.
Operational maintenance, I mean, how often are you having to clean these? I see birds are flying around, and the water which is
Once
on
or
there
twice
now.
a summer.
Okay.
That's about it.
And has any panel had to be replaced?
No.
Not yet?
No. So I've had people say to me, I mean, what good is solar? It's so expensive, not much power. You know, the Golden Gate Bridge was expensive to put in. The Civic Center was expensive to rebuild. Any of these projects that are really worth doing are worth stepping up to the plate for.
In fact, the combined solar and efficiency project at the Moscone Center saves San Francisco $200,000 a year on its electricity bill. But what about solar's impact in the developing world? Here is Martin Green, a world leader in silicon solar efficiency.
One of the strengths of the technology is that you can use it in areas that there's just no conventional supply of electricity. And there's about 2 billion people worldwide that don't have access to any electrical supplies at the moment.
Here in Africa, extending electrical lines through the countryside is usually too expensive. Without electricity, work and study largely stop at sundown. There's no fridge to preserve the food. Often the only source of light is from kerosene lamps, which are dangerous and polluting. They rely on imported oil and provide very little light. Kenya's location on the equator makes it ideal for solar power. And as people become more informed about the benefits of solar, more and more are interested in giving it a try. In the developing world, a single solar panel powering a light or a TV can make a world of difference for a family. It marks a new beginning for education and for connection to the wider world. Nepal is one of the poorest and most remote places on Earth. Many children work in the fields during the day, making education impossible. But an organization called Light Up the World is offering a cost-effective solution. These white LED lights consume a tiny fraction of the power needed by a regular light bulb. They are powered by batteries charged by small solar panels. So now families can gather for the evening meal without breathing kerosene fumes, and children at last have an opportunity to study in the evening. There are many uses for small-scale solar power in the developing world. For instance, many vaccines to prevent disease must be kept refrigerated. In East Africa, solar panels keep the precious medications cool, and UNICEF delivers the vaccines to remote communities by camel. The existence of solar power can be a matter of life and death. Take water, for example.
70% of the world population does not have safe drinking water. 75% of the diseases in the developing world come from bad water. So I think purification of water is another great application of this photovoltaics.
Coupling solar power to small pumps here in Nicaragua allows water purification where none was available before. This alone can revolutionize health and standard of living. In the fields, pumps can irrigate land that was once infertile. Villages become self-sufficient. Should governments be responsible for this transformation?
Providing energy is a necessary part of a government functioning, And it is also sort of a birthright of mankind. I think we should give him the minimum energy required for his use. So the governments have to provide. I don't see why not. I think we should see that the governments provide that minimum requirement.
What about the future? No one seriously suggests that solar power alone will transform the world's energy picture. It needs to be part of a whole package of renewable energy sources, including, of course, wind power. These giant turbines have operated in California's Altamont Pass for more than 20 years.
Wind energy is certainly the biggest energy producer today of clean energy, and it's the lowest cost by far. It will probably always be lower cost than solar cells. On the other hand, it'd be very difficult to supply the world's energy needs with wind. The machines are generally located in remote areas, so the energy has to be transported. So it's complementary in many ways to solar cells. Solar cells produce their energy during the day. Many wind systems produce energy at night. Solar cells produce their energy right where the energy is needed. Wind systems produce it far away.
In a more playful vein, the future might look like this. The Pathfinder is a solar-powered, remote-controlled flying wing developed by NASA. It weighs only 600 pounds and takes aerial photographs traveling at speeds up to 20 miles an hour. In the same spirit, experimental solar road vehicles are running races and endurance tests. No competition for today's cars, but they get the imagination going. Even amusement parks have gotten in on the act. Where once solar cells could only power a toy Ferris wheel, they now power the real thing on the end of Santa Monica Pier in California. But the future of solar power is much bigger than this.
It's true we don't supply much energy compared to coal and oil. Just a drop in the bucket compared to that. But on the other hand, it's growing very quickly, 30 to 35% per year, and today it's a $7 billion industry. So it's small compared to the energy requirements of the world, but it's becoming a serious industry in its own right.
When you look at the kinds of companies involved today and the kinds of horsepower that are being brought to bear here, I think the Sharps and the Shells and the BPs and the GEs, these are companies that make things happen, and I think the rate of adoption and the rate of implementation and the rate of it becoming a big piece of the energy picture is just happening now.
I would be very much surprised if in 50 years' time solar energy is not responsible for something between 25 and 35% of the entire electrical power globally used.
What will permit the industry to grow so big? Steeply rising fuel costs, of course, and new, ever more cost-effective solar technology.
This is one of SunPower's recent solar cells. It's very efficient, about 50% more efficient than a standard solar cell, but it's similar. It's made out of a silicon wafer. This is a wafer. If you were to compare this wafer with the wafer a cell was made out of 20 years ago, it's much thinner. You can flex it like this. It's as thin as a piece of paper almost. And so one of the things that's happened to bring the cost of solar down is that these wafers get thinner and thinner.
The most efficient and innovative solar technology is still used in space applications, where cost is less of a concern than reliability, low weight, and long life.
This new type of the cell is not silicon, but the thickness of the cell is 1 micron. So it's quite flexible and very light. So it is quite useful for the space application.
The most efficient solar modules made today are in the space program. They run about 34–35% efficient. So those are very expensive. They would not be really useful or helpful for the homeowner or for the business owner.
Slashing costs for everyday solar applications is now the main goal for many in the photovoltaic industry. The secret of this may be how you fabricate the silicon.
And the biggest thing that you can do to make these costs get cheaper is to do continuous processes.
Bill Yerkes, who designed the first solar panel to go to the moon, has recently launched a company that makes silicon wafers far more efficiently.
That's what we're trying to do here, very much like Henry Ford did in the car business, to make them on a continuous basis with all interchangeable parts. A typical crystal grower might grow 1 megawatt of solar panels per year, and ours will do 5 megawatts per year. So when we have 12 of these growers in here, we'll be able to make 60 megawatts a year of wafers for photovoltaic manufacturing.
Although increasing the efficiency of producing traditional solar cells may lower costs significantly, some believe that this is not enough.
There needs to be a different way, a simpler way, a lower cost way, a way to make very large format renewable energy available to anyone, anywhere.
Here in the lovingly preserved industrial landscape of Lowell, Massachusetts, a startup company is attempting to rewrite the rule book of photovoltaics. They're not using silicon at all. The scientists here believe that a completely new material may be required for mass use. They're experimenting with long-chain polymers, organic plastics which can absorb light and change it into electricity. The basic material looks and feels a lot like old-fashioned film.
So what we're doing in many ways is borrowing from the photographic film industry. We're taking very, very small nanometer, tens of nanometer size particles, polymers, and being able to coat them in a controlled way and be able to print or coat the whole device.
These new materials would both harvest the light and conduct the electricity.
So one of the applications we look at are things like fabric. So being able to print or coat on a very, very large web. So now you can think about the garments that you wear or the things that you carry, from a woman's handbag to your shirt to an army uniform, being a power generator. Built in, you put it on or you carry it with you in the normal way that you would.
The next step, and the most important step, is to get this technology to the point where it is a real commercial product. And that should never be underestimated in difficulty. There are so many problems that you run into on the way, each one of which in time you can solve, or typically, or hopefully one can solve. But it's still a long way from discovery to commercialization.
Scientists believe that within the next 30 years, we shall see technical breakthroughs that will revolutionize solar power, whether it's based on silicon or something else. Well, what will the power of the sun do for us? Will it become a major part of the solution to the world's energy problems? Will it bring light and clean water to people all over the developing world? And will it help us deal with global warming? Well, that all depends on our developing a better and cheaper technology, of course, but it also depends on how we think about it. If a sustainable future really matters to us, and if we really care about how we leave the planet for our children and our grandchildren, then I personally think we should take the power of the sun pretty seriously. What about you? Are you going to be part of the solution?
I still feel that what we're doing is changing the world, and I still feel every day that I go in that I make a difference, and that there is a thing that we're working on that will leave a better future for everybody that inhabits the world. So it's with a lot of pride that I tell people what I do.
I'm optimistic that solar energy will contribute a significant fraction of the energy needs of this country. I think it's time that we focused on that as a goal. I think it's time that our government stated that as a goal.
I'm convinced that energy is one of the make or break challenges of our times. Unless we put our minds to it, the second half of the century is going to be the beginning of a worldwide disaster. On the other hand, if we do put our minds to it, I'm convinced we can look forward to a better future. And solar energy is going to be part of that solution.